Okay, so thanks for coming, everyone. Let's get started. Thanks for your patience. Okay, so it's a pleasure here to introduce my friend and colleague, Mike Boylan, Kolchin. And he is currently a professor at the University of Texas at Austin in the astronomy department. Before he came to Austin, he graduated with his PhD from the University of California at Berkeley around the same time I did. I won't tell everyone the year because we're getting that old. From that point, he moved to Germany to do a postdoc at the MPA, where he was one of the main contributors to the Millennium dark matter simulation and played fundamental roles in the development of that simulation. And this is a simulation that's very influential in the astronomical community. From there, he came back to the US, where he was a fellow at the University of California at Irvine for a few years. And after being a fellow at the University of California at Irvine, he took a faculty position in astronomy at the University of Maryland. His services were called for here in the great state of Texas a few years later. So he moved to Texas a couple of years after being in Maryland. So he became an assistant professor at Austin, and now he's an associate professor, full professor probably at some point soon. So Mike is one of the foremost experts on cosmological simulations and sort of how they connect to observations, and particular emphasis on local group and formation of Milky Way, dwarf galaxies, globular clusters, as he'll talk about today. He has a bunch of really highly cited papers. I won't go through and name them all, but he's actually done an incredible amount of influential work. So let's thank Mike for being here. And before I forget, which I certainly will, here's our gift to you, the speaker. You may or may not use this, up to you, but you can take it home if you want.
All right, wow, yeah.
Okay, thanks, Mike. So go ahead and start whenever you're ready.
Okay, well, thanks for that nice introduction, Louis. Makes me feel a lot better about myself, actually. Usually that's not how I think of myself, so I definitely appreciate that, and I appreciate everybody being here. It's really nice to actually be in person for a visit. Hasn't happened to me for over 2 years, so I'm sure every speaker who's been here has been saying that, or many of them. But what I'd like to do is talk about stars and cosmology and how they intersect. I think it's an interesting question to me because this is something that's been historically used a lot, but at present, people typically think of the cosmic microwave background as the gold standard for cosmology. And I'll try to tell you why I think that, of course, it is a gold standard, but the information content there isn't the only information content. We should make sure that we're using other information content about the universe as well. So I was going to do from stars to cosmology, but then I saw after I submitted the abstract a few things like this. So there was a paper out last week about claim detection of an individual star in a galaxy at redshift 6.2 that's highly lensed and directly detected in Hubble imaging. Okay, and so you often read things like this in press releases. This is the discovery of the furthest and earliest star ever seen, a dot of light that's shown 12.9 billion years ago, or just 900 million years after the Big Bang. That means the light has traveled for 12.9 billion light years to reach Earth. So what they really mean is we assumed the Lambda Cdm model, right? We found something that we think is at redshift 6.2, and we incorrectly computed the distance. Okay, the universe is expanding, so something that's traveled for 12.9 billion years isn't 12.9 billion light years away. But anyway, I think the point here being there's no fundamental way to get a time for these kind of observations. Okay, the time, this 12.9 billion years ago, the 900 million years after the Big Bang, they both assume a relationship between this observed redshift and a cosmological and something else. So it takes a cosmological model to go from this redshift to an age. All right. So this redshift is the primary observable in cosmology, and the mapping from that redshift, or equivalently the scale factor, which is just the measure of how big the universe is relative to its size today. So when the universe was half the size, the scale factor A is equal to 2. That's it. Is equal to a half. Redshift is equal to 1. That requires a cosmological model, this mapping between redshift and time. Okay. So the only actual way we have to do time is through something like nuclear reactions. That's the only actual measurable time that we have in the universe. So stars give an alternate way to measure time, one that's based on primarily nuclear reaction rates. And so part of what I'd like to talk about is the discovery space where the stellar and cosmological chronologies can intersect and what we can learn from that. And so hopefully that'll be of interest. So the starting point is the Friedman equation, which when I teach undergrad cosmology, I say, I'm not advocating, tattooing anything on yourself, but if you're going to choose one equation to tattoo on yourself, you should choose this one from this class, okay? And okay, so hopefully no one's done it yet, but the point is that this is a really fundamental equation, and I think encapsulates most of the cosmological thinking that we have, because what it tells us is that the rate the universe is expanding, this Hubble parameter, h of a, is just directly related to the matter and energy content of the universe at that time. And what's hidden in here is it's also related to the geometry of the universe. So this is basically encapsulating general relativity. We have a fundamental connection between the expansion rate and the matter and energy content of the universe. So how fast the universe is expanding depends on the kinds of matter and energy in it. So it depends on what this sum goes over, right? So we might have non-relativistic matter, which just scales like the volume. We might have radiation, which drops off faster than the volume because you also have the redshifting of the radiation as the universe expands. We might have the cosmological constant, which is cosmologically constant, other things as well. Okay. And how much that matter and energy dilute as the universe expands depends on the kind of matter and energy it is. Right? So this is just what I was saying here, that matter scales like the volume. Radiation density goes faster in terms of the scale factor or the redshift. Cosmological constant is just constant. So I think the key thing to note about this is once you've specified what's in the universe at one cosmological epoch and how that changes with redshift, it specifies all the components of the energy at any other time. And that specifies the expansion rate at any other time. So this is a tremendously powerful equation in a sense, because it tells you, once you know what's in the universe at one point in time, and you know how that stuff changes with time, you know the expansion rate at any other time. Okay, so the Lambda Cdm model then basically says you can rewrite this this way. You take the expansion rate and you say it's equal to the expansion rate today, that's h naught squared. And then it depends on these little omega things, and I'll come to that in a second. So this assumes the Lambda Cdm model, so that the only components are matter, radiation, cosmological constant, and potentially curvature of the universe. So h naught is this Hubble constant, 100 little h kilometers per second per megaparsec. So it's how fast things are the universe is expanding at the present day. And these omegas are just a fractional contribution to the density. So it's like taking a pie chart and just saying what fraction of that pie chart is in matter, in radiation, in cosmological constant, whatever. And observations I'll show you basically say that this curvature term is negligible today. So it's even simpler. There's only 3 real terms that we need to worry about: the matter density, the radiation density, and the cosmological constant. So if we do this today, the pie chart tells us what these omegas are. So the fraction of the pie, so dark energy dominates. Dark matter and atoms are smaller fractions, and radiation is not even visible on here. Okay, the radiation content of the universe today is dominated by the cosmic microwave background, and that's true at all times, and that's negligible. So where do we get this information from? You might think the best place to look is the nearest by, and that's normally what I do in my day job, which is also astronomy. But I think about the local groups, the very nearby stuff. But it turns out that the best place to measure these values is not today; it's at the very early universe. So actually, go back and measure this at some other time. And again, that then establishes things at the present time if you assume this cosmological model. How do we do this? Well, this microwave background, if you remember, is basically coming from when the light in the universe last interacted with matter. This is the surface of last scattering. The universe cools and cools, and as it does, It means that eventually photons don't scatter off of electrons anymore, and they stream freely towards us. Imprinted in that is the slight temperature difference that different parts of the universe had, because the universe was slightly denser or slightly less dense in that region. Okay, so these are micro Kelvin fluctuations, and you can see that basically this is not kind of random fluctuation. There's a characteristic scale if we zoom in on this, and that characteristic scale is equal to the distance that a sound wave could travel in the early universe. So these are acoustic oscillations in this photon baryon plasma that was tightly coupled until the radiation streamed freely. So we can sort of basically say that there's one characteristic scale here, and that's the sound horizon, right? And if you do a Fourier decomposition, basically, this is a spherical or harmonic decomposition because it's all sky, but same idea. You do indeed get this kind of harmonic series, okay? And from this series, what you get is the scale, the angular scale of that sound horizon, okay? And that tells you something about the geometry of the universe. And you also get relative heights of the peaks here, okay? And how those heights depend on the matter and energy content of the universe is, as you change the amount of dark matter versus normal matter, you change how the photon baryon fluid compresses and rarefies in the gravitational potential wells that existed in the early universe. Okay, so so basically the scale here and the spacings set the angular size of the sound horizon. Then from the peak heights, you understand the matter density as it's split up into cold dark matter and baryonic matter. And then that actually fixes the physical sound horizon. Once you have the physical sound horizon and the angular sound horizon, you use triangles and you basically say, how far away is this thing? How far away this is depends on the Hubble parameter. So this is where the Hubble parameter comes in. And that's where the cosmic microwave background gets this Hubble constant. It's not directly measuring the expansion rate today because the information is imprinted 300,000 years after the Big Bang, some probably 13.8 billion years ago. But since we're observing sort of this at some distance, we're using that lever arm to understand what the Hubble parameter today is. So again, if we take this pie chart, normally what we're doing here is the pie chart as a function of scale factor, which remember is just 1 over 1 plus the redshift. If we do it today, we said that basically dark energy is dominating, okay? But it's only dominated in the very recent past. As we go back in time, we see that matter dominates, and then earlier radiation dominates. So if I go back to the time of the CMB, we're looking at a time when neutrinos and photons contributed 25% of the energy density of the universe. Atoms contributed 12%, dark matter contributed 63%. So that's sort of this point on this kind of plot. And dark energy wasn't there at all. And that's why the CMB doesn't really constrain dark energy in any way. Okay, but so this basically says if I know the energy content of the universe at that time, I know what the expansion rate was. That was the Friedman equation. And then I can make a prediction at all other times. So I extrapolate that forward, and that's how you get that Hubble parameter today. Right? So just knowing these numbers at early times allows you to calculate what the expansion rate should be today. And that's 67.36 plus or minus 0.54 kilometers per second per megaparsec. So a sub 1% measurement of the expansion rate today based on an extrapolation from the measurements of that value at a redshift of 1090 when the universe was 1,000 times smaller than it is. So you've heard about the era of precision cosmology. That's what people mean, right? So these are the parameters, the baryonic density, density of normal matter, the density of cold dark matter, the Hubble constant. They're all known to something like 1% precision or better based on properties of those maps of the cosmic microwave background. Again, this is all assuming what they call the base lambda cold dark matter model, which has 6 parameters, a couple of hidden parameters, and a flat geometry. So the other thing I want to draw your attention to here is this is why people say we know the age of the universe. If you assume this model and you take the microwave background, You can calculate that the age of the universe is 13.797 billion years, plus or minus 23 million years. This is an extremely precise measurement of the age of the universe. So this is why people take this for granted, okay? If you assume this Lambda Cdm cosmology and take the microwave background maps that Planck has, you have measured the age of the universe to almost 0.1%. Okay, so again, if you go back to this Friedman equation, for a flat model, near the present day, radiation doesn't contribute. So the difference in the total density is just comes from the matter density. So basically, everything is in either cosmological constant or matter today. So you can substitute this in here. And so the way we get this is just by integrating this Friedman equation. So this is just a differential equation for that scale factor. And so we just integrate, and that gives us a relationship between the scale factor and the time. So this is where times come in from these kind of models. Okay. So then the full interpretation is the contents of the universe tell us how it's been expanding as a function of time. If you know the contents at any one time, you know the expansion rate at any other time. And then that gives you a unique mapping between that the size of the universe and the time of the universe at that size, the time since the Big Bang. Okay. And for low redshift, this mapping only depends on the Hubble parameter and the matter density of the universe at a fixed expansion factor or at a fixed redshift. As you can see, it scales inversely with the Hubble parameter. Okay, so people here are much bigger, much more expert on this question of how we measure the Hubble constant locally, but I wanted to get into this as well because this is the source of some of the issue that I want to talk about. And that is, we don't have to just take this for granted. We can actually try to measure how fast the universe is expanding nearby. And that goes in the opposite direction, right? So not trying to understand properties at redshift of 1,000 when the universe was 300,000 years old, but trying to take properties very nearby and then get out into cosmological distances where galaxies are receding away from us as with the expansion of the universe. So to do that, basically what you do is you take the one absolute distance measurement we can do, which is parallax. Okay, and you do that parallax that measures how far away a certain type of object is. Could be a Cepheid variable star, anything that will allow you to go further out in the universe, and you can calibrate that. That means you know the distance luminosity relationship between that object. Then you take that object and you say, okay, now that I know how bright the relationship between distance and brightness for that object, let's go find more distant things where I have one of those objects and something that can be seen really, really far away, a type 1a supernova. So that calibrates the type 1a supernovae to the Cepheids, which have been calibrated to the parallax. And then you go really, really far away and you say that the universe should just be expanding like in the Friedman equation. Since I've measured the connection between the brightness of the supernova, the brightness of the Cepheid variable, and the distance of the Cepheid variable, I can measure the expansion rate. All right, so you can put that on the same plot then. And if you do, it shows up right here. And I think that this looks great, but this is, I think a wise person once said you could hide a multitude of sins on a log-log plot. Right? And that's, maybe it's not a multitude of sins, but you have to zoom in to see this. But if you take these error bars seriously, there's an enormous discrepancy here, some 5 sigma discrepancy. I just heard today this W boson mass discrepancy is 7 sigma, so I'm going to drop all of this anyway. So sorry, this is the last time I'll ever talk about this. So this is something that people have been thinking about a lot. This has been firmly established that using these Cepheid variables as calibrators, there is a discrepancy between the predicted expansion rate based on the most detailed measurements of the contents of the universe at a time when density fluctuations were very linear and easy to compute, versus today when things are very lumpy, but we can actually sit here and measure things well. So this is the discrepancy. Computing the present day expansion rate, 67 kilometers per second per megaparsec. And the units are kind of annoying, but don't worry too much about them. The point is the discrepancy. And the measurement gives you something that is formally 5 sigma away. So there is an inconsistency in the model or in the data. The extrapolated expansion rate of the universe is not the same as the measured expansion rate of the universe. And this goes by the name of the Hubble tension. Great. So one way we can see this is by plotting it in terms of the measured value of omega matter and H naught. Remember that in the low redshift universe, all that matters for the expansion rate is the normalization, H naught, and the matter density. So if you plot the cosmology, this is what the CMB says. It's this very narrow ellipse. Locally, we don't actually have a great way to measure the global matter density because of the inhomogeneities of the universe. But we know what the expansion rate is. And this is the discrepancy here. All right. So what could be happening? There could be errors in terms of on either side, right? And I'll talk a little bit about that potentially at the end. But let's take this discrepancy seriously. So one way you could actually get the model back to being a consistent one is to change this expansion rate, right? So if you change the energy contents of the universe, you'll change the expansion rate, and maybe you can get back to what we were before. So this is the evolution of that pie chart that I showed you before. And just as an example, one thing that you can do that seems to work well, or least poorly, as it was put in a couple of papers, is to add a little bit of dark energy at early times. So please do not ask me why one would want to do this. What is the physical model? Particle theorists are infinitely clever, and so there are particle physics models for this that involve axion-like fields, and there's even motivations for this now from string theory. But the point is, if you do this, where you allow some form of dark energy to be 10% of the energy density a little bit before the time of the microwave backgrounds, when the universe was 3,000 times smaller than today, not 1,000 times smaller than today, then you change the inferences that we've done before, okay? And if you change those inferences, well, that actually changes things on this plot. And really what's happening is you allow a little bit of early dark energy, the universe expands faster slightly. That means it hits the redshift of the microwave background a little bit earlier. So that sound horizon is a little bit smaller. The angular size of the sound horizon is really, really well measured by the CMB. So if you decrease the angular size of the sound horizon, you also have to decrease the distance to the sound horizon. That means you have to increase the Hubble parameter. And so that's why you get a Hubble parameter that is, instead of being 67, it's something like, could be 70, could be 72 or 73. You start to get an overlap here. So that's positive. What does this mean for the age of the universe? So if you do this age, again, Planck gives you this very precise measurement. Shoes tells you nothing about the age of the universe, again, because it's just measuring the expansion rate. That doesn't tell you nothing, but it doesn't pin this down. But now if you add early dark energy in, you get this kind of contour. So the price of resolving this Hubble tension, or a price you pay with this early dark energy, and again, I'm just using this as an example model, is that you end up with a universe that's between 700 million years and 1 billion years younger than the Planck universe. Okay? So, and again, I want to emphasize this early dark energy model seems to be as consistent with the data as the Lambda Cdm model, the base Lambda Cdm model. So you're not paying a penalty for doing this in that sense. So this is 2 models that have equally good fit to the data. And there's a difference in a gigayear or a few hundred million years of the age of the universe. So the statistical error is very small. The systematic error, I would argue, is still quite large. Again, because what I'm saying is you just put 10% at most of the energy density of the universe in some kind of dark energy for a very brief instant, 50,000 years after the Big Bang, and then just let it die away. That changes the age of the universe by 1 billion years. Okay, tell me how easy that's going to be to measure. So, I think the point is, on the one hand, the CMB is this treasure trove, and it's extremely well constrained. The fact that that's all you can do and still be consistent with the CMB is amazing. But I think it also says that some of these numbers, the precision isn't the whole story. The accuracy is very important here as well. And remember, it's not just the age of the universe. The whole thing goes, you're normalizing something that's basically changing the expansion rate. So it changes the relationship between the age and the size of the universe, or the age and the redshift at all times. Okay, so now we've got the same differential equation, but we've just added this extra little term here. And so that changes the relationship between time and redshift. And I had another plot for this, but this one showed up today because there was a Redshift 13 galaxy candidate. So I thought I'd just show this one, but it's very common to show these plots that use them interchangeably, right? Time and redshift. So here you see redshift 0, the present day, the Big Bang. Here's our famous 13.8 billion years. And they say, look, redshift 13.3 corresponds to 13.5 billion years, redshift 11. It's 13.4. There's a one-to-one correlation here, right? But again, that's assuming a very specific model. And you see this all over the place. And I wanted to put one of these in that I'm actually on just to say that I'm guilty of this too. But these assume a connection, right? And I think there's a good reason for that. The cosmology has been thought to be very good and to show this tight connection between redshift and time. So anytime you see these two axes, that says I've assumed a way to get between redshift and time, or time and redshift. And this goes both ways, right? This is a measurement where they're doing things with galaxies, they're measuring redshifts. Here, this is something where they're measuring the ages of stars and then trying to put that into a cosmological context. So just to be a little more precise about what this means, if you look at very early times, you say, let's take a fixed look back time. So if I go look back 5 billion years ago, what redshift does that correspond to? In the Planck cosmology, you can see here, it's, I don't know, redshift of 0.6. And it's about redshift of 0.6 in early dark energy. At small look back times nearby, there's no difference, which is good. You don't want to say that things are very different in terms of how long ago something happened between these two models. But if you start going further and further out, it's very different. So for example, redshift 12.5, that's close to that oldest galaxy I just showed you. That would be, you can see here, redshift 5 or something versus redshift 7. 12.9, closer to that galaxy, is now redshift 13 versus redshift 6. And if that galaxy is actually there at redshift of 13, you can see what that would mean in terms of time for early dark energy. It'd be around this 12.9 billion years. Whereas in Planck, redshift 13, you'd have to go way down this plot. It would probably be, well, you saw 13.4 or 5 billion years. So the further away you go, the bigger the change you get in a redshift at a fixed, the bigger change you get in a redshift at a fixed look back time. So what does this mean? Well, let's just say I have a hypothetical star cluster that has a known age, okay? It would correspond to very different formation times in these two kind of models. So if I say I know something is 12.75 billion years old, in the Planck cosmology, that might live at redshift 5 with an error bar at full width is delta redshift of 2. Whereas for the early dark energy model, that thing could have formed at redshift 15. And note, these are disjoint in terms of time. So if I'm making predictions that somebody can go out and make an observation for their telescope, it's going to come in at a fixed redshift. And so it'll maybe be able to differentiate these two. Similarly, if I say what redshift is the highest redshift galaxy, well, I made this plot before that candidate showed up today. But here you can see that the highest redshift galaxy candidate was at redshift 11. That might have been 12.5 billion years versus 13.3, 13.4. Same thing. There are differences here, and these are actually minimizing the differences in some sense. There are early dark energy models that have wider splits here. So how well do we know this time age of the universe and this redshift time relation? So I'd say basically there's a 4.4% uncertainty, fundamental floor in the uncertainty here in the relationship between redshift and look back time. as long as early dark energy or something like it is viable as a solution to the Hubble tension. So as long as we don't understand where the Hubble tension is coming from, and there are cosmological models that change the energy content of the universe and can explain it, we shouldn't be taking this 0.17% number seriously as the fundamental of how precisely we know the age of the universe. The accuracy is something like 4%. That's saying there are different models that would give you a different age. All right, so what's the other way? Well, we talked about this a little bit. You run into problems if the universe is younger than the oldest objects in the universe, so we don't want that. And the first low mass stars that formed, if they formed right after the Big Bang, they should still be around today. And that's because the lifetime of a star depends sensitively on its mass. The lower mass a star, the longer the lifetime. So if we can measure stellar ages, we can set a lower limit to the age of the universe by saying we better find the universe to be older than the oldest things in it. So a good place to look for this is globular clusters. These are collections, dense collections of stars. This seem to be very old. So this is a typical old globular cluster. It's one of the most nearby ones, which is why I'm showing it here. If you look at a Hubble image, it's actually quite beautiful. Very dense collection of stars. And again, the idea is if you plot the luminosity of a star as a function of its surface temperature, you can sort of do a mapping between the lifetime and the mass of the star directly. So our sun sits here, it has a lifetime of 10 billion years. Much more massive stars, by a factor of 10, might only live for 10 million years. And stars that are less massive, by a factor of 3, will live longer than the age of the universe. I'm not going to say the universe is 10 times longer than we thought it was. So basically, if you measure all of these globular clusters and see where they turn off of this hydrogen burning main sequence, you can use that turnoff point as basically saying which stars have died. They all formed at the same time, so that tells you the age of that cluster. I would say this is Astro 301, and it is, so I stole this from a lecture that I gave last year. But so basically you can see this is one cluster that's quite young. It still has a lot of fairly massive stars. This is a cluster down here that's much older. It's all of these stars have burned through their hydrogen fuel as well and have left the main sequence. So again, the issue is you need to understand the absolute luminosity of the stars there. So we get back to this issue of getting to a distance. But for these very close globular clusters, we can measure distances with parallax again. And so the idea is parallax gives us the distance. That gives us the absolute magnitude where the stars are turning off of that main sequence. And that gives us the age. And they report an age in this paper of 13.4 billion years with a statistical error of 700 million years and a systematic error of 1.2 billion. And there are a whole bunch of places you can find systematics. But there are 2 points. The first is if you take this seriously, just look at the central value, it's already sort of larger than the age of the universe for these early dark matter models. And the second is that I think these numbers can come down, okay? And so if you can do this better with smaller error bars here, you might be able to say these models are not viable for solving the Hubble tension, and therefore this whole colloquium up to this point has been a waste of my time, and I should have just been napping like usual. Okay, so I think the missing piece so far in this is how to connect up globular clusters to an actual cosmological context. So when do they actually form? If globular clusters form late in the universe and they're very old, then you have an even bigger problem. You have to account for all of that. So when do we expect globular clusters to form? Well, there are a couple of models, a couple of classes of models. There are many, many models, and everybody who's made them, they all hate me. That's the main thing they have in common. No, that's not true. They all hate each other also. But this has been a contentious field for a long time. But I'll group these into 2 kinds of models: galactic models, which is basically where globular clusters form in turbulent gas-rich disks. And again, that's sort of a reasonable idea because these globular clusters are very, very dense knots of stars. You need very high surface density of gas, very high pressure to do that. And so gas-rich disks are a great place for that. And that would predict that they form at redshift 2 to 4 or so. So something like 11 billion years ago in that Planck cosmology. The other kind of model is links these to specific conditions in the early universe, well, earlier universe, not sort of CMB era. And in this case, maybe they'd be forming in the reionization era, basically, redshift 6 to 10, something like that. So maybe different by a billion years in this cosmology. And this would explain the very old ages that people have measured, and also the low metallicities of the stars and the spatial and kinematic distribution around the Milky Way. So just to give you a sense of this, these are a couple of kind of galactic models. And they're both doing the same kind of thing. This shows you the median formation history. And for globular clusters, you can see this kind of happens here at redshift 2. And they've done the same thing, right? They've assumed some kind of correlation. Yep, right, good. Here, same thing, typical as a function of mass now is at redshift 2-ish, 2 to 3. These would be the pre-galactic models. This one says the formation rate peaks at redshift 11 or something like that. And this one says it peaks at redshift 9, maybe here. So this is their best fitting reference model. It's right here. Okay. So I would argue, now I can get back to more of my wheelhouse, which is nearby galaxies and star systems. Do globular clusters in these nearby galaxies and low mass systems hold the answer? And part of the reason I wonder that is if you look at star formation and how it depends on the mass of the halo that the galaxy is forming in, it's very nonlinear. So low mass dark matter halos are inefficient at turning gas into stars. So are high mass dark matter halos, but there's a peak in the center here at the Milky Way mass. If you look at globular clusters, though, the efficiency is independent of the dark matter halo mass. This is that same plot. Now, if I only look at the stars that are in globular clusters in that system and not in all other star formation. So somehow globular cluster star formation is a tracer of halo mass, whereas all star formation is not. Okay? And what that means is the relationship between the mass of a globular cluster and the mass of globular cluster stars and the mass of all stars in a system has to have this sort of inverse shape. And this is, you should not take this as data, right? This is just me in PowerPoint flipping the plot. So that's why it looks very similar. But it has to be something like this if you want to come out with this relation between globular cluster mass and halo mass. So somehow a larger fraction of stars in these low mass galaxies are formed in these globular clusters. In fact, this is the Fornax dwarf spheroidal galaxy. It was quote unquote discovered in the 30s, but the globular clusters that are known to live within it were known in the 1800s. Okay, so this is a kind of a galaxy that was technically discovered before the galaxy itself was known. The globular clusters were seen first because of their high surface brightness. It's something like 3 × 10⁷ solar masses, so pretty puny. Remember, the Milky Way is maybe 1,000 times more massive than this in stars. Eridanus 2 is undeniably puny. It has a total stellar mass of 50,000 times the mass of the sun. It has a central globular cluster. It's offset from the direct center, but it's near the center. It holds something like 5% of the stellar mass of this object. Again, in the Milky Way, we're talking about 0.1% or less of the stars in the Milky Way are these old globular cluster stars. So we've been working on this from a simulation point of view. So we've simulated 7 dwarf galaxy dark matter halos. They're a dwarf galaxy in the sense that they are dwarf galaxy today. So they're low mass at all cosmic times. 10⁻⁻⁰ solar masses in halo mass today. That's a factor of 100 lower in mass than the Milky Way's dark matter halo mass, we think. And we find that 6 of the 7 halos form these globular cluster candidates. And again, they're much more consistent with this idea of a pre-galactic kind of sense of things and not the galactic disk sense of things. So here's kind of what happens in one. This is the highest redshift of formation. It forms a 2 × 10⁵ solar mass dark matter halo. This is something like 1/100th of all the baryons in this system at that time end up in stars and globular clusters. What happens is there's lots of accretion. These are showing the surface density of gas. So lots of accretion early on, go here to here to here. You get to very high density, and a few stars start to form somewhere. They send off stellar feedback, which compresses the gas even further. You get a cluster that forms right here. Okay, that's shown in the zoom in. And then the feedback from that cluster blows all the gas away very quickly. So within 10 million years after the first star in this system forms, all of the gas is blown off because so many stars are forming in a tiny region. And this is that newly formed globular cluster. This is another example. In this case, you can see it's actually two patches of the interstellar medium of the galaxy just smashing together and forming this globular cluster. Same mass, a little bit lower redshift, but same result. And in fact, you can see here, this one sends this shock wave out that compresses the gas in the galaxy itself and leads to additional star formation. So there's a lot going on here. If I ask, where is this globular cluster forming? These are the stars that existed before in cyan in this system. And the globular cluster is forming, well, not where those stars are. So this sort of circle shows you the half mass radius of those stars. The globular cluster is forming outside of any kind of existing stellar body. Again, there's not much to speak of here anyway, but it's not like the globular cluster is forming in the dense center of a dark matter halo. It's forming where the gas is dense, and the gas density is distributed over a much larger range than the dark matter density. This is the slightly lower redshift version. Here you see a bit more of a pre-existing galaxy, but again, the globular cluster is forming well outside of the half-light radius. The globular cluster stars are in red in this case. So basically, the formation precedes the formation of any discernible galaxy. The clusters form well away from the center of any dark matter halo, so they don't have any dark matter in them, which is consistent with observations of globular clusters. They form out of gas that's higher metallicity than the pre-existing stars, and we think that's why we're able to do this at high redshift, whereas other models try to do it at lower redshift. It's not gas that's tied to the mean metallicity of the galaxy, it's actually pre-enriched gas. They're often significantly contributing to other star formation as well, the formation of these clusters. The high fraction of stars in these clusters at early times is consistent with the observations that we see around us today, that these low mass galaxies have these big fractions of stars and globular clusters. And the properties are also consistent with Hubble observations of lensing fields, which basically show very dense small knots in lots of these things. So let me come back to that point. These things in formation should be bright for tens of millions of years in the UV. So young stars are very hot. Young massive stars shine predominantly in the UV. And so these things that form 10 to the 5 solar masses of stars in a very short window will be pretty bright. This is all relative, okay? So this is beyond what can actually be done directly. But this is detectable in gravitational lensing fields with James Webb Space Telescope. Things that are a bit more massive. So there are globular clusters. There's a range of masses. There are things like this in the Milky Way. They're actually at the edge of what's detectable in the Hubble Deep Field, and they should absolutely be detectable in JWST images. So the deepest ones are covering an area of something like a square arc minute, and they should be able to see these kinds of things. And the most massive ones that we see in the Milky Way should be able to see easily. Okay, so the question is, how common are these? And I think ludicrously common is maybe the right word. So there's 2 per cubic megaparsec nearby, which basically means there's 10 to the 7 per square degree, or every arc second of the sky that you look at, there's a globular cluster there, right? So you won't catch it in formation most of the time, but there's a lot of arc seconds on the sky. And so you should be able to see these things. We think the Webb telescope should detect hundreds to thousands of these in formation. I'll skip over that. I guess the one thing I'll say is, don't worry about the plots too much, but the point is that we can start to constrain physics of the formation of these things as well. That is, there's some models that say they must have been 10 times more massive at birth. And if that's the case, we should have seen them in the Hubble Deep Field in big numbers. So I think we're already saying with these kind of observations that these globular clusters aren't forming and then losing a huge amount of mass. So I think putting it all together, James Webb Space Telescope will tell us about the when of globular cluster formation, and that's in terms of redshift, right? So we can actually go out and measure the redshift where these things are typically forming. Locally, things like Gaia, Webb, and Hubble, along with improved stellar models and higher dimensional sampling algorithms that are now common, can reduce the uncertainty of the when in terms of ages, right? So now we're getting a redshift and an age, and we might be able to match these up. So I think that if we combine these in 5 years, we may have a much more complete and consistent picture of how, when, and where globular clusters form, both in terms of redshift and in terms of look-back time. So 2 independent handles on the same quantity. And again, this could be important for our understanding of cosmology from the first part of the talk. So if the oldest globular clusters are reliably measurable to be older than 13 billion years, then you can't really modify the base Lambda Cdm model with these things like early dark energy that solve the Hubble tension, because they're only going to make the universe younger. So if you can really reliably say there are these very old things in the universe, that really constrains not just the precision, but the accuracy or the model space that you should need to explore for the cosmological models. Right, so takeaway points. Again, this is an issue of precision versus accuracy for the age of the universe, right? Cosmological parameters are known extremely precisely, but that's all in the context of this one cosmological model, and it fits very well. But there are other plausible models, a little bit contrived, that can also fit well and give you different numbers, okay? So the cosmological model could be wrong, it could be incomplete. And again, a very small change, 10% of the energy density in dark energy at redshift of 3000 changes the age of the universe by 7–8%. So at present, the precision is 0.2%, but the accuracy is 20 times worse, I'd say. For stars, the precision is a little bit worse. The accuracy is also a bit worse. But I think there's a lot more room for improvement in the stellar side of this than in the cosmology side. And globular clusters are an alternate route to this chronology because we understand their ages based on how hydrogen burns in stars and calibratable things in the very nearby universe. We're now able to form these plausible globular cluster candidates in cosmological simulations. And we're finding very high formation redshifts, reasonably high anyway, not these sort of galactic models that say they form around the time of the peak cosmic star formation rate density. So this is a prediction for James Webb, right? And we think that Webb should see globular clusters as they're forming, and that will establish directly the typical redshift of formation. So path for improvement is more data. It's rare that path for improvement is less data, but I really feel pretty strongly in this case that more data is going to be a big help. The accuracy may reach the same level as cosmological observations in the next years. One place where you can really gain is that Gaia distances will establish a sort of parallax standard that's much better than what's currently done. And so that helps you relate the distance to the absolute luminosity for these globular clusters, so you know where that main sequence turnoff is. Cosmology, there's a whole bunch of other measurements, most of which in the local universe are also a bit higher than the cosmological measurements with the CMB. And so trying to really understand, is there any systematic there is important. And again, JWST and Gaia data are very important for that. And I think we still need to explore systematics in the CMB. The CMB is, I think, still is a gold standard, but just because it's been the gold standard doesn't mean there couldn't be something we don't quite understand. So it's still important to explore that with the current and future data. So I'd say that stars to do cosmology is something that's very 1950s, but I'm hoping it's also 2020s. So I'll stop there. Thank you.
Mike, for a great talk. So I'm monitoring the Zoom. Is there any questions either locally or on the Zoom? So a question from Grisha, and we'll go to Darren. Could you repeat the question for people on Zoom?
Yeah, so the question is, I gave an example of this early dark energy model, and I said you have to basically introduce this early dark energy at a very specific redshift of 3000 or so. Could you do this at redshift 10 to the 7, redshift 10 to the 8? Would that do anything? You could introduce it there, but I think that constraining power is much less, and it wouldn't help this scenario. And the reason is you need to change that sound horizon by 4 or 5 co-moving megaparsecs. And if you introduce a little bit of early dark energy at very, very early times, the universe doesn't have enough time to grow even close to that much. So it'd be very close to the standard model of cosmology if you introduce dark energy, early dark energy at that time. You have to do something after the sound horizon is grown to the size difference, at least, that you care about in these two models. So it turns out that there's this sweet spot at around redshift of 3500, which is right around the redshift of matter radiation equality. And I think that's related to some of the parameters you measure in the CMB through the Sachs-Wolf, integrated Sachs-Wolf effect and a couple of other things. So it's not 100% clear to me why it's picking out exactly redshift of 3500, but that's really where you have to do it. It has to be pretty close to the CMB, but before it, so not much earlier.
Oh, go to Darren here. Could you paraphrase?
Yeah, so I think the question is, basically you need to, it doesn't really matter exactly what you do. You need to change the sound horizon by a little bit. And you have to, if you want to solve it with these early-ish universe physics. And so it's not really this specific model. It's just anything that you do that changes the sound horizon by 4 or 5%, makes it 4 or 5% smaller, makes Hubble constant 4 or 5% bigger. And I basically agree with that, unless there's some other observation. And so I've only talked about CMB. So this doesn't help you with growth of structure, where there's a slight tension as well. That's a whole nother talk that somebody else better give, because I don't have one ready for it. So I've only stuck to that kind of aspect. But I agree that this is sort of a placeholder model, and it's just very hard to do this. And one generic consequence is you're going to reduce the age of the universe in all those models.
Justin, and then we got a couple questions on Zoom. Justin, go ahead.
Yeah, so the question is, when we're doing the simulations of cluster formation, how do we distribute the mass of stars forming as a function of the stellar mass? And what we do is we use the standard model so far, which is basically it samples perfectly from a pre-established initial mass function. So we use simulation particles that aren't individual stars. So a simulation particle might have 500 solar masses, and that has contributions from stars that sample an IMF. And so we could do things where we actually randomly sample from that IMF and see if that makes a big difference. And I think that will make a difference on the individual basis, right? How long does it take for a cluster to form here? How much is the feedback? The feedback depends on the mass of the star. So I think that will make a difference there. But I think what this is saying is globally, it probably, at least this is, somewhere in the universe, you should get something that looks probably like that. And so this is not a terrible approximation as a first one, but I agree we should do more careful sampling.
More question from Alexei Belyan, and then we can go to Zoom.
Yes. Right. So I guess if you really find a star that you feel very confidently is 13.7 billion years old, then you better not change the cosmology to match the Hubble tension. What else could you possibly do? The lazy thing is to blame either the observers at the high redshift universe or the low redshift universe. And I think, so I don't really have a great proposal. People have spent a lot of time. There are thousands of papers now thinking about how do you resolve this discrepancy. And it's just not very easy to do it with the current understanding that we have. There's a narrow window to do it with high redshift solutions. It's very difficult to do it with low redshift solutions. So as I think I alluded to, these kind of models are sort of the best of the worst, if you will, or the worst of the best. I don't know. These are the ones that work, but nobody's sort of very excited about them in a sense because they're a bit contrived. And you're sort of in this very strange part of parameter space. And it's not obvious how to do much better than that, unfortunately, if this tension is real. And that's why I think people are very excited about thinking about this so far.
Okay, so we have two questions on Zoom here. We'll go in the order here. So Rob and then Nick. So Rob, go ahead.
Yeah, thanks for great talk. In thinking about your formation channel for globular clusters at very high redshifts, can't help but kind of extrapolate a step further and speculate whether this could also be the channel for producing sort of seed supermassive black holes. Have you thought about that, or do you think they're two completely separate problems?
Yeah, thanks for that. So I think that, so the question was, you know, we're trying to do these models and seeing that there are these channels for high redshift formation. Could this also be a channel for formation of high redshift black holes at this redshift or even earlier? I think it's definitely a very interesting question. And I think well, there are a couple of angles one could take. The first is, you know, if we had black hole seeds in some of these systems, would we have then further fueling from these kind of very compact star forming regions, or could we get in very low metallicity gas or zero metallicity gas direct collapse black hole? And I think that would be a very interesting way forward. I think the other interesting avenue is thinking about how this would tie in to predictions for gravitational wave measurements of sources, since a lot of them are thought to be in globular clusters. This tells you the sort of dynamical time delay that you need between when the globular clusters form and when these binaries, let's say, merge, which isn't exactly your question, but I think it is a related and interesting one on the black hole side. So I think that's a cheap way of saying we haven't done any work on this, but I think the direct collapse black hole one is a very intriguing one.
Great, thanks.
Okay, thanks. We'll take one more question from Nick on the Zoom. Go ahead.
Hi, great talk. I have to say that invoking dark energy a third time seems desperate to me, but that's just my own opinion. It's like 2 times is bad enough, but 3 times, I don't know. Also, the Hubble constant is extrapolated from redshift of 1080 to today with absolutely no change in the universe. So we assume the universe is cleanly evolving over that time period, which also to me seems remarkable. But those are opinions. 2 questions is, why are there no very metal poor globular clusters? The most metal poor globular cluster is at minus 2.4 roughly. Also, there used to be, and I'm not up on this at all, there used to be a relationship between the mean metallicity of globular clusters and the mass of the galaxy. I don't know if that still exists, but if that's true, that would seem like it'd be hard to explain with very early globular clusters forming. Do you have any comments on those 2 points?
Yeah, maybe I'll take the second one first, which is there used to be at least a connection between the mass of the galaxy and the metallicity of the globular clusters. And I think that you're right in the sense that this would not explain all of the globular clusters. This would explain the metal poor globular clusters, I think. And metal rich globular clusters probably would form in something like that, more like that galactic phase. And then that would explain both why you only see only metal poor globular clusters in very low mass galaxies like dwarfs, and why you see the sort of trend you have with the mass. And I think then the other question was related to what's the lowest metallicity of globular clusters it's observed, if I'm remembering. And so that, as far as I know, people are starting to find very low mass globular clusters that are maybe even below this minus 2.5, so something like metallicity of -3 with respect to solar, but they're all sort of very low mass and tentative detections in Andromeda and the Milky Way. So I think that future surveys, just in the next few years, will really kind of clear this up a little bit better. And I think there's a lot of interesting parameter space there. There are a lot of stellar streams that seem to be lower metallicity like that, like maybe -3. So it might be that these things form, but they're just too low mass to live for a Hubble time. They dissolve, and so that's why we don't see anything below that, or don't see many things below that metallicity.
Great, thanks. So any other quick questions for Mike? Okay, so with that, let's thank Mike again for a great talk. Lots of good questions. We'll see you next week.